Welcome to the deep dive. Today we are diving into source material that focuses on a technology aiming to, well, turn your clothes into a source of power.
That's right.
We're looking at something called texTENG, which is a user-friendly framework for making wearable textile-based triboelectric nanogenerators, or TENGs.
And this is a truly significant development. The core problem texTENG is trying to solve is how to harness the energy we generate all the time just by moving.
Okay.
So a TENG's function is to convert that mechanical energy from human motion into electric power. It does this through contact electrification and electrostatic induction between two layers of material.
That concept alone, turning simple movement into a reliable energy stream, could be transformative for wearable tech. The sources suggest that TENGs have, until now, been quite complex.
Oh, very much so. Confined to labs requiring custom materials you just can't buy off the shelf.
So the mission of texTENG is to change that. It introduces this comprehensive design menu, bridging the gap for the HCI and maker communities.
Exactly. And to appreciate how accessible they've made this, we should probably touch on the foundational physics first. The system works on contact electrification.
Right.
You have two distinct materials. When they touch, the triboelectric effect causes them to generate equal and opposite electrical charges on their surfaces.
But if those charged layers just stayed together, nothing would happen, electrically speaking. So the magic must be in the separation and return.
It is. That separation of the charged surfaces induces a potential difference, a voltage.
Okay.
And that voltage difference is what compels electrons to flow between the electrodes attached to the materials. When they come back together, the electrons flow back. That cycle, driven by movement, generates an alternating current.
And that's the output you can harness.
That's the output.
So motion is the key ingredient, but human motion is so varied. A finger tap is not a knee bend. How does the framework account for that?
It does so through three primary modes of operation, each optimized for wearables. The first one is probably the most intuitive, the vertical contact separation mode.
So a direct press and release.
Precisely. The motion is perpendicular to the interface. Imagine just pushing two fabric swatches together and pulling them apart. This mode is great for high-power outputs.
Then you have the second mode, which adapts to friction, the lateral sliding mode.
Correct. Here, the displacement is parallel to the interface. Power is generated because the sliding changes the effective contact area between the surfaces.
So that would be perfect for, say, fabric layers sliding over each other.
Yes, the inner thigh while walking, or a sleeve rubbing against the torso.
And the final one, which seems the most flexible for garment integration, is the single electrode mode, SE mode.
The SE mode is a simplification. You only need one TENG layer relative to a grounded reference. In a wearable context, human skin itself often acts as that second moving triboelectric layer.
Ah, I see.
It's exceptionally useful for harvesting energy from, say, a finger tapping a smart textile.
All these principles are then synthesized into the core of texTENG, the design menu. This must be the key to democratizing the technology.
It is. The menu curates material selection and fabrication techniques. It takes the difficult material science and translates it into something repeatable.
On that note, material selection is vital. Performance hinges on pairing materials with opposite triboelectric polarities. What did the evaluations find to be the best pair?
They found that a combination of core shell PTFE, which is highly tribonegative, and spandex, which is tribopositive, gave the highest overall power performance.
That makes sense for power, but what about wearability? Comfort, sustainability? Did the menu address those priorities?
It certainly did. For direct skin contact, silk is recommended. It's soft, breathable, and natural.
And for sustainability?
The framework proposes acrylic as a recyclable alternative to PTFE in some cases, so it's balancing performance with more eco-conscious design.
Very smart. Now let's walk through the structural dimensions, which are based on familiar crafting techniques. We can start small with the 1D structures, the yarn-based ones.
These are fabricated using standard methods, braiding, twisting, coating. They are the fundamental building blocks.
And from those yarns, you can create either of the main 10 configurations.
That's right. You can make single electrode or SE configurations by sheathing a conductive core with a triboelectric layer, or you can make contact separation or CS setups by braiding two of those SE yarns together.
Then we scale up to 2D structures, entire textiles, weaving and knitting. Why choose one over the other?
It's all about the application. Weaving, using something like a plain weave or a twill, gives you stability and abrasion resistance.
For durable patches, maybe?
Exactly. Knitting, on the other hand, yields elastic fabrics, much better for places that need flexibility, like an elbow or a knee.
This is where the framework introduces a significant jump, the 2.5D structures. What is the functional gain of adding that half dimension?
The primary advantage is optimizing the power output. With standard 2D structures, the tribal layers are often too close together, which limits the potential difference. These 2.5D structures, using something like a double weave or an Ottoman stitch, inherently optimize the distance between the layers. That slight separation significantly enhances the contact separation mode.
So they're using standard textile geometry to solve a fundamental physics problem in the TENG design.
That's the elegance of it. And that dimensionality also enables new functions, like flex sensing, where the output changes based on how much the fabric is bent.
Let's bring this to life with some of the practical applications, starting with self-powered sensing.
They had some excellent examples. One was a touch-sensitive drawstring made by coating conductive thread with PDMS. It operated in SE mode.
Just from a finger touch.
Yes. And it produced an average output of 3.1 volts.
3 volts is quite substantial. What could you do with that?
You could directly interface with a low-power microcontroller or trigger a wireless signal to, say, toggle a smart light, all without a battery.
Wow.
Another was an interactive hair extension, a CS yarn structure that could activate a voice assistant with a simple press. It yielded 1.8 volts.
Beyond these subtle inputs, what about larger body movements?
For movement sensors, the research showed a woven flex sensor, a 2.5D structure, on the wrist.
What was it used for?
It was used to control a game just by flexing the wrist. It generated about 1.18 volts upon interaction.
And there was a knitted elbow patch as well.
Yes, a 2.5D patch. It used near-field electrostatic induction for wireless interaction. When the user rested the patch on an external electrode, the movement created a signal averaging 0.95 volts.
So it's useful for sensing, but the bigger question is always energy harvesting. Can these things actually power electronic devices?
The source material addresses that directly. They built an energy-harvesting smart garment with 2 woven swatches, each 100 millimeter square, stitched under the arm.
And as the arm swings?
As the arm swings, the lateral sliding generates continuous power, and it successfully powered a low-power digital watch continuously.
That's a direct proof of concept, but the actuation example seems even more powerful, the smart socks.
That prototype used a tubular knit structure, optimized for vertical contact separation during the impact of running.
Okay.
During that motion, the socks generated an average peak voltage of 13.2 volts.
13 volts from a sock. That's a remarkable figure. How was that voltage managed and used?
It was stored in a capacitor. Once enough charge built up, it was discharged in a short burst, powerful enough to flash 20 series-connected low-power LEDs in an armband.
A self-powered running light, essentially.
A clear path toward it, yes.
Let's turn to the technical performance, because consistency is critical for wearables. What about the dynamics of motion?
Well, the testing confirmed that the PTFE and Standex pair gave the highest performance. But crucially, the evaluation showed how user movement affects charging efficiency.
What did they find was optimal in terms of force and frequency?
They confirmed that higher force and frequency led to faster and greater voltage storage. The sweet spot was around 10 newtons of force at a frequency of 4 hertz.
And what kind of human activity does that represent?
It's roughly the intensity of a brisk walk or an easy jog. So it's efficient even during moderate routine activity.
And under those conditions?
The system charged a 47 microfarad capacitor to about 1.7 volts after 5 minutes.
And for user input, were the touch sensors dependable?
They were. Both 1D and 2D touch sensors provided a robust signal-to-noise ratio, consistently above 15 for all participants, which is essential for reliability.
To manage this unique output, high voltage, low current, the framework needs special hardware. Let's start with the board for sensing.
That custom board needs a specific signal conditioning path. First, you need voltage rectification to convert the AC signal to DC, then voltage attenuation, which just reduces the signal so microcontroller can safely read it.
And what's the most critical step for interfacing with standard electronics?
That would be impedance conversion. TENGs has a very high impedance. Microcontrollers need a low impedance input, so an operational amplifier is used to perform this critical mismatch correction.
Got it. And for energy harvesting, the hardware gets more complex. You need a full power management system, a PMS.
That's correct. The PMS takes those sporadic bursts and turns them into a steady voltage. It starts with a rectifier and an initial storage unit.
And then there's a specialized switch.
Precisely. It includes a silicon-controlled rectifier and a Zener diode. Its job is to ensure energy is only released when the voltage is at its peak to maximize efficiency.
And from the switch.
From the switch, the energy goes to a buck converter, which steps down the voltage and releases it steadily to the load.
So to pull this all together, what are the key design recommendations? If someone wanted to build one, what should they prioritize?
The structure. Woven textiles are best for locations prone to abrasion and friction, underarms, thighs. Knitted structures are preferred for applications needing flexibility, like at the joints.
And for maximizing pure energy generation.
You should target body movements with high frequency and force. So the best performance comes from devices in socks and shoes, or garments between the thighs.
Finally, let's place texting in that broader context of sustainable wearable computing.
A key part of that is durability. Using materials like PTFE-based fabrics, which resist water and wear, makes the TENGs practical for long-term, real-world use. The goal is for them to be invisible, durable parts of our clothing.
The framework provides this incredible roadmap, but it also raises a deeper challenge. While one texteng can power a small device, fully battery-free operation for, say, a smartphone would require aggregating energy from multiple devices. So the provocative thought we leave you with is this. If you were designing a full wearable ensemble today, how might you strategically place and structure multiple texting devices across the body to maximize and aggregate that total energy harvest?
A profound design challenge indeed, for the future of truly seamless personal power generation.
This deep dive shows the potential for textile-based energy harvesting to integrate invisibly into our daily lives. Thank you for joining us.